Hello. So now we will study the impulsive force by efflux velocity. So you see, when we are having a tank, and in that tank if we made a hole, the liquid is going out, and the velocity of this liquid which is going out will be 2gh. H is this that we already learned. So when this liquid is going out, it is gaining some velocity. Why it is gaining some velocity? Because see, if you see these 2 points, when liquid is at this point, its velocity is similar to the velocity of the upper layer and above that. So at this point, the liquid is moving with 0 velocity. Its velocity is approximately 0 here. And when this liquid is coming out, it is gaining the velocity, and that velocity becomes under root 2gh. You see? So inside this hole, the liquid is at rest, and outside the hole, it is moving with some non-zero velocity. So when this liquid is passing through this hole, it is experiencing an impulsive force which makes its momentum from 0 to some non-zero value. So that impulse is applied onto the liquid by this vessel. This vessel is applying that, or the part of vessel basically. That impulse is applied onto that liquid by the other liquid, this liquid. But this liquid is a part of the vessel, so this force will be applied by, impulsive force will be applied by this whole vessel. So this whole vessel will apply the impulsive force onto this liquid. Action reaction if you believe in, and we have to believe in that. So if you believe the action reaction, so this impulsive force is applied by this, and the same force but in opposite direction will be applied by the liquid onto this whole system. So we want to calculate that impulsive force. Okay. So as you know, the impulse J is equals to delta P. That's the formula. Not the impulsive force, but the J. The J is equals to delta P, that is the formula. So what we do, let's assume some mass of the liquid here. And that mass, I'm saying it is dm mass, a small mass. So that dm mass passes through the hole in dt time. In dt time, that dm mass passes through the hole and it comes out and it achieves the velocity under root 2gh. So this is my test volume or test mass. When it was inside, it was having 0 velocity. When it went outside, its velocity becomes non-zero. And it goes outside in dt time. Okay. So for the test volume, the initial momentum was dm multiplied with 0 because its velocity was 0. And when this comes outside, its momentum becomes dm multiplied with ve. Okay. So the impulse experienced by this dm mass will be equals to p final minus p initial from this formula. So that value will become ve times of dm. This is the impulse applied by the vessel onto the liquid. Okay. So as we know, this J is also equals to F average dot dt. This F average is the average impulsive force applied during this process. So the thing is, during this process, force is not average, it is not constant, it is a variable force, but that variable force we cannot calculate. So what we do, we equate this value, F average, we define this F average corresponding to this. This formula we have seen in conservation of momentum. So if this J value I replace it by, this J value if I equate with the upper equation, then I can say the F average multiplied with dt will be equals to ve dm. Or we can say F average will be equals to ve dm by dt. This dm by dt is nothing but rate of flow of mass. So this rate of flow of mass, if you remember in the continuity theorem, we studied this concept. In continuity theorem, from this is equation 1. So from continuity theorem, this dm by dt there we calculated, and that value was equals to density multiplied with this cross section area multiplied with the velocity when it is coming out. So this is the velocity it is coming out, ve. So I can replace this value here. So F average, impulsive average force, can be written as ve multiplied with rho small a ve, and that becomes rho small a ve square, F average, value of F average. So if we replace the value of ve, this will become rho a under 2gh square, and that will give us 2gh. And that will make this value of average force as 2g rho small a times of h. That's the average impulsive force applied by the vessel onto the liquid. And as you can see, this average impulsive force depends upon the density, it depends upon the cross-section area, and it depends upon the value of h. If you increase the cross-section area, average impulsive force is going to increase. Along with that, if you increase the density of this fluid, again it is going to increase, and the h also. As we will go down, average impulsive force will also increase. And this is the average impulsive force applied by the vessel onto the liquid. If from the action reaction, you can further deduct that this is the same force applied by the liquid onto the vessel. So if this average force, which is applied onto the liquid, is in this direction, F average, I'm calling it 1, the same amount of average force will be applied by the liquid onto the vessel, but in opposite direction. And as you can see, this average force, which is applied by the liquid onto the vessel, may cause some motion. So if this will cause some motion, there will be forces which will be acting there to prevent the motion. Because if there is a friction, if we study this system, this half average now, if for a time being, if we start studying this vessel, onto this vessel there are 4 forces which are acting. One is the mg, obviously, which is acting at the center of mass of this whole system. One is the normal action, which is acting from the base in upward direction. One is this half average, which is acting applied by the liquid, outgoing liquid onto the vessel, and one might be the friction if friction is available. You see. So along the horizontal there will be only 2 forces. One, F average, which will become the driving force, which might cause the motion, and there will be some friction force which we might require to prevent the motion. So if there is a friction force, it will be acting in opposite direction. I'm calling it F, not Fk, because we don't know this F average, whether this F average is more than Fk or not. Because if this F average is more than Fk, then the motion will happen. If the F average is not more than Fk, then there will be static friction which will be acting at the bottom, and that will prevent the motion. Okay. So that thing we'll study during the examples. Okay. So here we learn average force applied by the outgoing liquid onto the vessel, and that outgoing force, this impulsive force by the outgoing liquid might cause the motion for this vessel. Okay.